Hi Shashank. We'll start the session in a couple of minutes.
Okay.
Okay. So we'll start the live session now. Uh, so the format is the same as previous classes for these live sessions. I'll first discuss a few MCQs. I'll first present an MCQ and I'll ask you to attempt the MCQ. Then I'll discuss each and every option in detail and the concepts related to the MCQ. Uh, so just mute you. If you have any questions, you can unmute yourself and ask me, uh, or you can type it in the chat box here. So I hope you can hear me. Is my audible?
Yes, yes.
Okay. Okay. So let's get started. Okay. So last week we were discussing week 4 questions. So we stopped at question 9. So we'll continue from question 10. Uh, this is the question. A Renshaw cell always inhibits only the alpha motor neuron that activated it, inhibits the alpha and gamma motor neurons of that muscle only, inhibits the alpha and gamma motor neuronal pool of that muscle as well as the agonist muscle, or D inhibits the alpha and gamma motor neuronal pool of that muscle as well as other antagonist muscle. You can take around 30 seconds to answer this. You can type your option in the chat box and then we'll discuss this in detail. I'm just setting a timer for 30 seconds. Okay, let's see what the response is. D. Okay. Okay. We'll just discuss this now. Let me just go to start inking. Okay. A Renshaw cell is basically it inhibits. Let us just see what the scenario is. So we have a muscle here, okay, and we have an alpha motor neuron, that activates this muscle. So this is an alpha motor neuron. So whenever this alpha motor neuron fires, the muscle contracts. So just uh, uh, close to the cell body of the alpha motor neuron, there's one more axon terminal that branches out, and this basically excites some another interneuron called a Renshaw cell. So this is a Renshaw cell. Okay. So this is a Renshaw cell, and what the Renshaw cell does is it has a that one of its fibers, one of its axons, go and inhibit. So this is inhibit the alpha motor neuron that itself excited it in the first place. So this is a form of negative feedback. So this kind of feedback is called as recurrent inhibition. So this is a Renshaw cell, and uh, it basically inhibits the alpha motor neuron that excited it in the first place. So this is a form of control mechanism, and the Renshaw cell itself uh, gets input from various other sources. For example, there are descending inputs that controls the gain of this Renshaw cell. Uh, so we won't discuss that. So in this question, it inhibits. First of all, we can. So basically, a Renshaw cell is an inhibitory interneuron. So it inhibits the alpha motor neuron that excited it. Plus, it inhibits the uh, alpha motor neuronal pool, which belong to which this alpha motor neuron belongs. So this motor neuron pool will have other alpha motor neurons that innervate this particular muscle, and it will also have gamma motor neurons that innervate this particular muscle. So the answer is it inhibits the alpha and gamma motor neuron pool of that muscle, as well as the other agonist muscles. So other muscles, so this motor neuronal pool will also have muscles that will also have alpha motor neurons which assist in the agonist muscles action. So for example, uh, let us consider an example of a biceps muscle. So when we do the action of uh, flexion, let me just open the. Yeah, so this is the biceps muscle. So when we want to flex, the biceps contracts and this happens. This action happens. So a bicep is basically for the movement of flexion of the elbow at the elbow joint. The bicep is the agonist. Also, there are other muscles that are also involved in flexion. So biceps is not the only muscle. There are other muscles also involved. So they are also the agonist. They are also agonist muscles in flexion. Uh, so let me just go back. So the answer should be it inhibits the alpha and gamma motor neuronal pool of that muscle as well as other agonist muscles. So the answer is C. Okay. So we'll go to the next question now. In case you have any doubts, you can ask me. Okay, so which of the following is true for surface EMG measurement? A. Measures activity of specific group of muscle fibers. B. Electrodes do not interfere with natural functions. C. Optimum choice for nerve conduction and velocity tests. Or D. Inability to specifically monitor deep muscles. So again, I'll give 30 seconds to answer this. Okay, we're done with 30 seconds. Let's see what the response is. Okay, so you have responded with D. Uh, so you have responded with D. Okay. Okay, so let's see what these options are. A measures activity of specific group of muscle fibers. No, actually, since it's a surface EMG, the electrode covers a larger area, and hence this cannot be the answer. Electrodes do not interfere with the natural function. This is true to some extent because if so, there are basically two types of electrodes that are used to measure EMG. One is surface electrodes, and the other is needle EMG. So, in the case of needle EMG, when you actually insert the needle into the muscle, it's going to interfere with the natural function. But in the case of surface EMG, since it's on the surface, it's not going to interfere with the natural function of the muscle. So this is the correct answer. Then C, optimum choice for nerve conduction and velocity tests. This is true if this is for the case of needle EMG. For example, in diabetes and other disorders, this is a very important test, nerve conduction and velocity test. These parameters are affected, and using needle EMG, you can actually find out what is the nerve conduction and the conduction of the velocity. Then the inability to specifically monitor deep muscles. This is true. So in the case of needle EMG, you can actually insert the needle deep into the muscle and you can take measurements. But in the case of surface EMG, it's basically an ensemble of activity of various whatever is below the surface of, of various muscle fibers. Uh, so the final answer is B and D. Which of the following statements is slash are correct? Intrafusal fibers surround the extrafusal fibers and detect length. Extrafusal fibers surround intrafusal fibers and detect length. Intrafusal fibers are located at the center of the muscle spindle and detect length. Extrafusal fibers surround intrafusal fibers and produce force. So again, I'll give you around 30 seconds, and then we'll discuss this particular question. Okay, let's see what the response is. C and D. Okay, so let's discuss this. Which of the following statements is slash are correct? Uh, Intrafusal fibers surround the extrafusal fibers and detect length. So first of all, let us see what is the context of this question. So intrafusal fibers basically are fibers within the muscle spindle, and muscle spindles are these basically these sensors in our muscles, which are used to give the length of the which are used to determine the length of the muscle as well as uh, uh, the the velocity of contraction. So these muscle cells uh, are used. Once you know the length of the muscle, you can get a relatively good idea of the angle of the joint. And if you know the angle of the joint, you basically know the orientation of the body segments. For example, let's say you close your eyes and you're still aware of at what orientation your body segments are. So that is due to the muscle spindles, because of the information that is being sensed by the muscle spindles. Okay, so getting back to the question, we have these muscle spindles, and within the muscle spindles, we have these intrafusal fibers, and uh, outside of the muscle spindles, we have these extrafusal fibers, and these. So this is how it is. Let us say this is a muscle spindle, So we have these intrafusal fibers here, and then we have extrafusal fibers, which is part of the muscle. So whenever these extrafusal fibers, like let's say they lengthen or contract, since this is in parallel, if intrafusal fibers either lengthen or decrease in length based on the length of the extrafusal fibers. So interfusal fibers surround the extrafusal fibers and detect length. This is not correct. Uh, Interfusal fibers do detect length, but they do not surround the extrafusal fibers. Extrafusal fibers surround the intrafusal fibers and detect length. So extrafusal fibers do surround the interfusal fibers, but they do not detect length. It's the intrafusal fibers that detect length. So basically, we have these sensors. We have afferent fibers going from the intrafusal fibers. So these are primary spindle endings and secondary spindle endings. So the primary spindle endings basically detect the length of the muscle as well as the velocity of contraction or velocity of change in length, whereas the secondary endings uh, detect only the length of the muscle. Okay, so getting back to this, intrafusal fibers are located at the center of the muscle spindle and detect length. This is correct. And extrafusal fibers surround the intrafusal fibers and produce force. This is also correct. So the answer is C and D. Yeah, I think Shashank got it right. Yeah, 100% correct, Shashank. Okay, moving on to the next question. Presynaptic inhibition is mainly caused due to A. Presence of inhibitory neurotransmitters like GABA. B. Excitation provided by another neuron, reducing the amount of acetylcholine released. C. Calcium channels already open even before the action potential arrives. Or D. Sodium channels already open even before the action potential arrives. Again, I'll give 30 seconds to answer this. Okay, let's see what the response is. Okay, Shashank is saying B, and Sai Madhav is also saying B. Okay, so you guys have responded with B. Okay, so let's see what the scenario that is happening here. So in an axon, in in a neuron, let us consider this as the axonal end bulb of the neuron. Okay, so an action potential usually travels down the axonal end bulb, and then uh, it opens calcium gated voltage gated calcium channels. Once the action potential reaches the end bulb, so there's a huge influx of calcium, and we have these vesicles here which detect the change in calcium. Okay, so there's a change in the amount of calcium concentration. So when this happens, there are these sensors on these vesicles. Uh, so these sensors start moving towards this particular membrane, the end of the membrane here, and then acetylcholine is released from these vesicles. So that is what happens. That's the normal working. Now what happens is, if you have, let's say, another neuron here, you have another neuron here which is basically exciting this particular region, the axonal end bulb. So what is happening is, this is leading to opening of calcium channels. Even let's say there's no action potential. So there's the calcium channels are opening because of this, and then there's some amount of calcium that is going in. So because of this particular neuron. So this is all happening in the presynaptic region, right? So this is the synapse and this is the postsynaptic region. So this can be another neuron, this can be a muscle fiber, the postsynaptic membrane. So since there is the calcium channels are already open and there's an influx of calcium, when the action potential actually arrives, what happens is that because these calcium voltage gated calcium channels are already open, only a few number of new voltage gated calcium channels will open up because some of them are already open. Hence, the amount of calcium that is going in will not be much. There's already calcium inside. So what these vesicles do is they detect a change in the normal function. They detect a change in the calcium level. But since there's already a level of calcium, there's already amount of calcium inside. The amount of change in the calcium concentration due to the action potential, this action potential, will not be much. Hence, what happens is these vesicles will not detect that change in a large amount of change in calcium, and hence they won't fuse with the membrane and release the acetylcholine. So that is what is happening here. So that is how inhibition is being maintained, is being achieved. So let us go through the options. Presence of inhibitory neurotransmitters like GABA. No, this is the case for postsynaptic inhibition. So we can also inhibit using inhibitory neurotransmitters like GABA at the postsynaptic membrane. B. Excitation provided by another neuron reducing an amount of acetylcholine release. This is correct. So this is what we saw. Then calcium channels already open even before the action potential arrives. Yes, this is also correct. We just saw this. And D, sodium channels already open even before the action potential arrives. No, it's the calcium channels. So the answer is B and C. So you guys are right. You got one option correct. Okay. So moving on to the next question. A Renshaw cell provides. Okay, is there a question? Yeah, Shashank. Yeah, you had a question, Shashank? You can unmute yourself and ask, or yeah.
Yeah. Uh, See, if on the presynaptic membrane there is another neuron which is causing opening of the calcium channels,
Correct.
that itself is going to cause release of neurotransmitter. Correct?
Yes. Yes.
Yeah. Then in that case, how can we say that opening of calcium channels is going to cause inhibition, presynaptic inhibition?
Okay. So
If my understanding is correct, what happens is that there are going to be certain types of neurons which cause presynaptic inhibition by releasing certain neurotransmitters, which will cause decrease in the opening of voltage gated calcium channels on the presynaptic neuron itself,
mhm.
and that in turn is going to prevent the what do you say, release of the neurotransmitter.
Okay.
That is my understanding. Please correct me if I'm wrong.
Okay. Okay. So first, I'll just explain this part again, and then we'll also discuss what you have just said. Okay. So like you rightly pointed out, if this particular neuron is causing these calcium channels to open up, then there is already since there's an influx of calcium,
Yeah,
there'll be anyways acetylcholine released, right? So that, yeah, I agree with that. But what my understanding of this is, uh, there can be two scenarios. I think it either maintains a level of after, like, let's say that these calcium channels are open, it maintains that level of it maintains it ensures that these calcium channels are always open. So that level of influx of calcium is always there. Okay. So initially, let's say it starts to inhibit initially. Uh, uh, so this causes these calcium channels open up, and initially there is a release of acetylcholine, okay, but then it maintains this opening of calcium channels, okay. So after this initial release, because these calcium channels are still open, uh, so there is an amount of Ca2 plus concentration that is maintained inside. Now when another action potential comes, it cannot open up more calcium channels because it's already open. Are you able to understand what I'm saying?
Yeah, slightly difficult to.
Mhm. So what I'm basically trying to say is, initially when the presynaptic neuron,
Mhm.
when this neuron initially when it excites this, it causes a depolarization here. Calcium channels open up, right? Uh, till this part, do you agree?
Yeah, yeah, that's fine. So
Yeah.
that in turn is going to lead to release of
Release
acetylcholine.
acetylcholine. Now,
Yes.
this does not finish its activity here. It continues to excite this region, and the calcium channels continue to be open. Okay.
So you mean to say it is more of a neuropeptide that is being released by this neuron?
I'm
It
not
is
exactly sure about how this mechanism happens, but
okay.
what I know is that it basically depolarizes this region, which causes
Hmm.
these calcium channels to remain open. Hence, the inside the axonal end bulb, the amount of calcium concentration is elevated, and it is maintained at that elevated state. So when a new action potential comes in, more action,
Hmm.
the difference in the
Levels of calcium.
yeah, levels of calcium won't be much due to these new action potentials. And what these vesicles detect is basically a change in the level of concentration.
Mhm.
So when that does not happen, there can't be a release of acetylcholine. This is my understanding, but like you also pointed out that there can be other mechanisms. Maybe I can check about that and maybe get back to you in the next class.
Okay, thank you.
Yeah. Okay. So moving on to the next question. A Renshaw cell provides A. Positive feedback, B. Negative feedback, C. Recurrent inhibition, or D. Excitation to alpha motor neurons. Uh, so I'll give you guys 30 seconds again, and then you can answer this. We'll discuss this. Okay, let's see what the response is. B and C. Okay, Shashank has responded B and C, and Madhav has responded C. Okay. Okay, so these are the two responses. So let's go through this. A Renshaw cell provides A, positive feedback. This is wrong. We know that a Renshaw cell gives negative feedback. B, negative feedback. This is correct. Correct. C, recurrent inhibition. This is also correct. Correct. And D, excitation to alpha motor neurons. This is wrong. Okay, so why is this called? Why is recurrent inhibition also correct? I'll explain that. So basically, the recurrent inhibition is basically when the alpha motor, since the alpha motor, when the alpha motor neuron fires, the Renshaw cell gets excited by the alpha motor neuron, and the Renshaw cell inhibits the alpha motor neuron that excited it. So this is called recurrent inhibition. Uh, so these two are the correct answers. Answers. B, C. Uh, Moving on to the next question. Which of the following statements is true? So I'll give you guys around 2 minutes to answer this. This is slightly bigger, and then we'll discuss this question. Okay, let's see the responses. Shashank is saying C, D, E, and F. Let's see this. Epidermis, dermis, and endodermis form the bottom, middle, and topmost layer of the skin, respectively. This is wrong. Then Meissner corpuscles are sensitive to quick changing pressure, whereas Pacinian corpuscles are sensitive to rapidly changing mechanical deformation. This is correct. Let's just open up the slide uh, and check this. So, Meissner corpuscles sensitive to quick changing pressure on a small area of the skin. Sensitive to quick, whereas Pacini corpuscles are sensitive to rapidly changing mechanical deformation. So, rapidly changing mechanical deformation. So, B is the correct answer. Then, Meissner corpuscles are sensitive to rapidly changing mechanical deformation, whereas Merkel disc sends vertical pressure on the skin surface. So, we have already seen that this is not the correct answer. We can verify this. So the Merkel disc are vertical pressure on the skin surface. This is correct, but the Meissner corpuscles are not correct. Uh, then D, epidermis, dermis, and endodermis form the top middle and bottom layer of the skin respectively. Uh, yes, this is correct. So then basically G becomes wrong because that's not the correct option. I mean correct order. Then Meissner corpuscles are sensitive to rapidly changing mechanical deformation, whereas Pacinian corpuscles are sensitive to rapidly changing pressure. This is wrong. Most of the cutaneous receptors are found near the hand and lip area. This is correct. And most of the cutaneous receptors are found near the leg and hand area. This is not correct. So this is why we see that fingertips and lip area are very sensitive to touch. Uh, so that is one of the reasons, right? So the answer is uh, B, D, and F. Okay. Going to the next question. Which of the following statements are false regarding muscle spindles? So again, I'll give you guys 2 minutes, and you can then we'll discuss this question. So remember that which of the following statements are false? So this is the trick in this question. Okay, let's see the responses. Shashank has responded with B and G. Okay. Uh, when the length of the extrafusal fibers change, the length of the intrafusal fibers remain constant. No, when the length of the extrafusal fiber change, the length of the intrafusal fibers also change. That is how the intrafusal fiber is detecting the is sensitive to changes in it's sensitive to changes in the length of the muscle, and we have the sensory endings at the center of these intrafusal fibers. So when the extrafusal fiber changes its length, the intrafusal fiber also changes its length, and this is detected by these sensory endings or afferents which are present in the intrafusal fiber. So this is wrong. Muscle spindles are innervated only by afferent neurons. This is also wrong. It's a wrong statement. They are innervated by afferent neurons. They are also innervated. So the afferent neurons are these, like I said, 1A afferents and two afferents. Uh, so, they are the primary spindle endings and the secondary spindle endings. They form the primary and the secondary spindle endings. Uh, so these are at the center of the intrafusal fibers and within the muscle spindle, and the center region is a non-contractile region. But we have gamma motor neurons which innervate the polar regions of the muscle spindle of the intrafusal fibers. So they're innervated by afferent neurons as well as gamma motor neurons. So this is a false statement. Alpha motor neurons are large diameter myelinated axons, whereas gamma motor neurons are small diameter myelinated axons. This is a correct statement. D. Alpha motor neurons are extrafusal muscle. Alpha motor neurons are extrafusal muscle activation signals, whereas gamma motor neurons are intrafusal muscle activation signals. This is correct. Uh, this is what we saw. This is what I just described in this for this option. The primary sensory endings innervate static nuclear back fibers and chain fibers only. Uh, Actually, the primary spindle. Okay, let us recall that the intrafusal fibers have uh, uh, so there are different types of fibers, types of intrafusal fibers. Intrafusal. So we have uh, chain fibers and we have back fibers, and then the back fibers are further divided into static back fibers and dynamic back fibers. So the static back fibers, the dynamic back fibers, and the chain fibers are all innervated by the 1A afferents, which have the primary sensory endings, and the secondary sensory endings, that is the afferents of the type 2, innervate only the chain fiber and the static back fiber. Okay, so this is a false statement. The secondary sensory endings innervate static and dynamic nuclear back fibers as well as chain fibers. This is also false because it innervates. This actually the primary sensory endings does that. So these are actually swapped here. Okay. If we had put secondary here in option E, then it would have been correct, and if we had put primary in F, it would have been correct. Then G, primary sensory endings sense both muscle length and velocity. This is a true statement. So the question is what which of the following statements are false? Okay, so A is false, B is false, C is correct, D is correct, E is false, and F is false. So the answer is A, B, E, and F. Okay. Moving on to the next question. In the context of motor neurons being influenced by inputs from the brainstem, which of the following statements are false? Okay, so remember this. I'll give you guys around 2 minutes, not 2 minutes, around 1 minute to answer this, and then we'll discuss this. Okay, let's see what the response is. Shashank has responded with F. Okay. Okay. Okay, let's go through this. The input current versus discharge rate of motor neurons becomes linear under the influence of inputs from the brainstem. So this is a false statement. Uh, so when these the brainstem has these release this monoaminergic have these monoaminergic neurons, which I think release, if I'm not wrong, uh, I'm not able to recall what exactly it releases. Yeah, serotonin and norepinephrine, and these basically activate these L-type calcium channels on the motor neurons, and then there's a huge influx of uh, current of calcium. So this influx of this inward current basically elevates the so when a new uh, action potential comes, or when a new depolarization happens, uh, due to these brainstem influences which I just described, uh, the input current gets basically the synaptic input current gets magnified by 5 to 10 times. So that's a high level overview of the functioning of these things, of the brainstem, how the brainstem influences uh, 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 the firing of these motor neurons. Anyways, getting back to this question, B, the input current versus discharge rate of the motor neurons becomes non-linear under the influence of inputs from the brainstem. This is actually a true statement. So initially what happens is you have firing of these motor neurons, uh, okay, and so you have basically a current. Let's say there's an input current that goes into a motor neuron, and that causes a discharge rate, right? Now, under the influence of these monoamine, so the more input current there is, the discharge rate increases proportionally. Uh, so there's a linear relationship. But in due to these monoaminergic inputs, this linear relationship is lost. So let us just uh, consider this as the input current, and let us consider this as the discharge rate. So under normal circumstances, the more the input current, the more is the discharge rate in the motor neuron. But under the influence of these monoaminergic inputs, this linear relationship is not there. There's a drastic increase in discharge rate, uh, of the order of 5 to 10 times due when there is an input current. So B is the B is the correct statement because it makes it non-linear. C, monoamine serotonin and norepinephrine released from the neurons in the brainstem activate L-type calcium channels on the dendrites of the motor neuron. This is a true statement. Monoamine serotonin and norepinephrine released from the neurons in the brainstem activate ligand-gated calcium channels in the dendrites of the motor neuron. This is false. E, the inward current in the motor neurons due to brainstem influences can enhance the synaptic currents by 5 to 10 folds. This is correct. And F, during sleep, the brainstem influences on the motor neurons are enhanced. This is false. Let me just, yeah, are enhanced. Actually, they are not enhanced during sleep. So basically, these brainstem influences causes persistent inward currents, which basically affect these slow twitch motor units to maintain posture. Uh, so I'll just show a diagram of this so that you get a better understanding. So we'll first finish this. So the answer is which of these statements are false? So A is false. D is false, and F is false. So answer is A, D, and F. Okay. Now let me just open up one of my note. One note, and I'll just show you a diagram which might give a better explanation of what is happening here. So you can find the diagram in Candle and Shorts. Let me just bring this here. Okay. So here's what happens. So in this particular case, the monoaminergic. So these are basically the diagram on top is an input current, and uh, input current in and the diagram below is basically voltage. So what happens is, uh, in the first case, the light blue plot, we the monoaminergic influence is less. So what happens is when there is an inward current, the voltage is does not reach threshold. Okay, and because the voltage does not reach threshold, there are no action potentials. But under the influence of monoaminergic input, what happens is, for the same excitation, the input current gets enhanced, it gets amplified, and so now this is the input current, and then you can see that there's a high rate of firing here that is happening. Then once the monoaminergic input is removed, there is still the influence of this monoaminergic input is still there, and due to which you can see that there is a the current does not go back to its original, the input current does not go back to its baseline. It's still sustained here, so there's a sustained tail current here, and that continues to fire, that is to lead to action potential. But you can see that the rate of action potential here is decreased. So you can just go through this in maybe Candle and Shorts, uh, and you can also read this, uh, the how the experiment was conducted. Okay, so going on to the next question. With regard to the sensory endings, innervating muscles, select the correct option. So I'll give you around 30 seconds to answer this, and then we'll discuss this. Okay, let's see what the response is. Shashank has responded with C. Okay, yeah. So basically, it's a straightforward question. The primary spindle endings belong to 1A afferent, belong to 1A, and secondary belong to 2. So the answer is C. Yeah, you're right, Shashank. Answer is C. Okay, going on to the next question. Which of the following statements are true? So I'll give you around 2 minutes to answer this, and then, or maybe 1 minute to answer this, and then we'll discuss this. Okay, let's see the response. Shashank has responded with C. Okay. Oh, okay. You have responded with F. Okay. Which of the following statements are true? The Weber-Fechner's law states that the perceived sensation relates to the magnitude of the stimulus by an exponential function. It actually relates to the magnitude of the stimulus by a log function. So this is wrong. The axons of the proprioceptor neuron serve as input as well as output to the cell body of the proprioceptor. This is a true statement. So we have a proprioceptor neuron here. So we know that it has like a T-shaped this thing structure. So these are the two axons of the proprioceptor. One has a sensory ending. Okay, so this goes to the body's periphery, and the other goes to the dorsal root into the spinal cord. Goes into the spinal cord through the dorsal root. So this goes to the spinal cord. So this is the correct answer because it gives input to the this thing. So so whenever there's a firing, whenever there's whatever modality this sensory ending senses, it'll start firing action potentials. So this conducts antidromically. This is called antidromic conduction, when the action potential travel in this direction towards the cell body. And so this is an input, and it also gives an output. So there is some sort of processing that is happening here, and then it conducts action potentials to the spinal cord. So this is orthodromically. This is orthodromic conduction, which is away from the cell body. Uh, C. So this is a correct option. So there's an output, there's an input as well as an output. C. During change in the length of the muscle, the secondary sensory endings in muscles do not change their firing frequency. Uh, During change in the length of the muscle, the secondary sensory endings in the muscle do not change their. Yes, that is because. So let us just assume that this is the length of the muscle. So this is a stretch that is happening in the muscle. So there is some sort of action potential here, but from the secondary sensory endings. But as soon as this change has become stable, you have a more faster action potential, which signifies the length of this particular muscle. But during the change itself, there is no change. There is no change in the action potential happening, right? So this is a correct statement because we know that secondary sensory endings only detect change in the length of the muscle, but not the velocity of change. During change in the length of the muscle, the primary sensory endings in the muscle do not change their firing frequency. This is not correct. During the change, they actually change their firing frequency, and uh, the velocity of the change determines what the firing frequency is during the change. So, for example, let's say we have a case here like this. Okay, so we have an action potential due to the primary sensory endings, and then we have this action potential like this, which is during the change. So there is a change in the there's a change in the velocity of the length. So during uh, this part, we have an action potential, and then we have. Now let us consider another case where the change in the velocity of the length is fast. So again, we have a action potential here due to the primary sensory ending. Then we have a rapid action potential here because compared to this, it's more higher because we know that primary sensory endings also sense a change in the velocity of shortening. So it's higher here because the velocity of shortening here is more, and then we have, which is similar to this part. So this part D is false because they do change during the change in the length of the muscle. E. The intrafusal fibers in muscles are innervated both by alpha motor neurons and gamma motor neurons. This is false. They are innervated only by gamma motor neurons. And F, the alpha motor neurons have a large diameter and the gamma motor neurons have a small diameter. This is true. Okay. So the correct options are B, C, and F. Let me just write that down. B, C, and F. Okay. So we'll stop the session here. Uh, I'll just open up the. So thank you for joining in, Shashank. And I hope this live session was helpful. And we'll kindly join in next week, and I'll also discuss that question that you asked me. I'll again go back and see. Uh, I'll further read upon that, and then we discuss it next week. So thank you for joining in. And what is your background, Shashank? From which? Can you just give an introduction about yourself? Are you from an engineering background or from a
No, no,
medical
I'm from
background?
a medical background. I'm from medical
Okay,
background.
okay,
Yeah.
okay, 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 Shashank.
Thank,
Thank you for
thanks,
joining in.
thanks a lot. Yeah,
Yeah. Okay. Bye. See you next week.
bye. Yeah, sure.